Today we're going to look at the properties of logarithms. Remember what a logarithm is. It's an exponent. That means that the rules of exponents apply. Let's go back and remember the rules of exponents. When we multiply, we add our powers on like bases. X cubed times x to the 7th, that's x to the 10th. When we divide, we subtract the powers on like bases. X to the 8th divided by x cubed, that's x to the 5th. 8 minus 3 is 5. And then we add the power rule. That's an exponent to an exponent, like x cubed to the 4th power. Quick reminder, that's x cubed times x cubed times x cubed times x cubed. And 3 plus 3 plus 3 plus 3 is x to the 12th, but we don't want to do this. We know the shortcut. When we have a power to a power, we multiply our exponents. As you learn the rules of logarithms, remember that when you multiply, you add the powers on like bases, that when you divide, you subtract the powers on like bases, and the power rule, when you have an exponent on an exponent, you multiply the exponents. The first rule, a logarithm is an exponent. Here I've got multiplication, and when you multiply, what do you do with your exponents? You add them. The log base b of m times n is a log base b of m plus the log base b of n. Let's take an example with a simple example with numbers. If I ask you to figure out the log of 100 times 1000, you'll notice there's no base. That means the base is 10. First thing I could do is I could multiply this. This is not applying the log rule though. And a 100 times 1000 is 100,000. And if I was asked to figure this out, it would be 10 to some power, 10 to some power is 100,000. Well, 10 to the 5th is 100,000. This is 5. 10 to the 5th is 100,000. Now let's apply the log rule and see if I get the same answer. This would be equal to the log base 10 of 100 plus the log base 10 of 1000. This means 10 to some power is 100, that's 2, plus this means 10 to some power is 1000, that's 3, and notice that 2 plus 3 is 5. You get 5, the same answer as if I just multiplied it all out. Again, when you multiply, what do you do with your exponents? You add them. Keep in mind, you might be asked to go the other direction. You might have two logarithms being added, and you might go back to here and rewrite it as a single logarithm. If you were asked to take the log base 3 of 9 plus the log base 3 of 27 and rewrite it as a single logarithm, you should be thinking, a logarithm is exponents. When do I add my exponents? Well, that's when I'm multiplying. This would be equal to the log base 3 of 9 times 27. 9 times 27 is 243. This is the log base 3 of 243. And that might be your answer. Now, notice 3 to some power is 243. That would be 5. 3 to the 5th power is 243. And notice that if you'd worked it out previously, 3 squared is 9, and 3 to the 3rd power is 27, and 2 plus 3 does equal 5. But for practice, you may be just asked to write it as a single logarithm, in which case this would be your answer. Second rule, the log base b of m divided by n. When you divide, what do you do with your exponents? You subtract. This is the log base b of m minus the log base b of n. And like the last question, you may be asked to go from here to here and rewrite something as a single logarithm. For example, if I asked you to write as a single logarithm, the log base 4 of 64 minus the log base 4 of 16, you could turn that into the log base 4 of 64 divided by 16. 64 divided by 16 is 4, so this is the log base 4 of 4. And if you were asked to write as a single logarithm, this would be your answer. But notice 4 to some power is 4. The answer to this would have been 1 if they wanted a single answer. And you would get the same answer if you worked it out here and here. 4 to what power is 64? Well, that's cubed. That's 4 cubed is 64. 4 to what power is 16? Well, that's 2. 4 to the second is 16. And 3 minus 2 is, of course, 1. The last rule here is the one we use most often to solve an equation with logarithms. The log base b of m to the power of n. Remember, a log is an exponent. What I have is an exponent to an exponent. That's the power rule. When you have a power to a power, an exponent to an exponent, what do you do with your exponents? You multiply. What this allows you to do is bring that n down, and you multiply your exponents. It's n times the log base b of m. Here's a simple example with numbers, and we'll do base 10. The log, this is base 10, of 100 cubed. What this rule says we can do is when I have an exponent to an exponent, that's the power rule, I multiply my exponents, I can bring this 3 down. This is 3 times the log of 100. Now remember, there's no base, it's base 10. 10 to some power is 100. 10 squared is 100. This is 3 times 2, and the answer is 6. If I hadn't done it that way, I could have said this. What is the log of 100 cubed? Well, 100 cubed is a million. 100 times 100 times 100. So this would have been the log base 10, there's no base, of 1 million. And 10 to some power is a million. Well, that's 10 to the 6th. 10 to the 6th power is 1 million. And you can see I get the same answer. An example of how this might be used just in practice, we'll use this to solve equations at some point, but here's a simple example. If I asked you to work out the log base 7 of 7 to the 5th power, I could take 7 to the 5th power, but that's going to be a really big number, and I don't need to. When I have an exponent on an exponent, because a log is an exponent, I can multiply my exponents. This is 5 times the log base 7 of 7. This means 7 to some power is 7. Well, 7 to the first power is 7. This is 5 times 1, which is 5. There are a couple odd rules that are in the book, properties, that are just shortcuts. And here are 2 examples. First one is the log base b of b to the x is x. It's actually fairly easy to see why this works, because remember how a logarithm is an exponent, and we could bring this down? Well, this would be x times the log base b of b. If I bring the x down, because I'm multiplying my exponents, take a look at this. This means that b to some power is b. Well, that would be 1. B to the first power would be b. This then is x times 1, which is x. This second property says that b to the power of log base b of x is equal to x. I can show you why this is, but it'll kind of blow your brain. Take a look at just this part of the expression. I'm going to go down here and look at just that. The log base b of x. Well, that's an exponent. What is the exponent? Let's call it a question mark. So this means that b to whatever my question mark is equal to x. Look at this last statement and think about it. These two statements are identical because this question mark represented the exponent that was this. In other words, this is b to that thing I don't know. And I already figured out that it would be x. Demonstrating this property is like a substitution. And if you can't wrap your head quite around that, just take a look at this. There'll be a couple of questions, and they're very easy to answer. They might look like this. So take a look at these two examples. We know that when we have an exponent to an exponent, that's what this is, that I can bring the exponent down. This will be 5 times the log base 3 of 3. 3 to some power is 3. Well, that's 1. This is 5 times 1, which is 5. But what they're saying is we can just skip all this and say, oh, right off, this is equal to 5. If we look at this, the log base 2 of 27, and it's equal to something, well, this means that 2 to that something is equal to 27. What we can do is just like a substitution, we can see that if we replace that thing we don't know with this, we would still get 27. We now have a shortcut. We don't need to worry about any of this. We can just immediately say that this is 27. These two properties aren't something we're going to use a lot. This next thing we learn is very important. Before I show you how to change a base of a logarithm, you need to understand how to solve a simple logarithmic equation. We use logarithms to solve for exponents. So let's solve an exponential equation. What you do to solve a logarithmic equation is take the log of both sides. The log of 4 to the power of x equals the log of 16,384. Notice there's no base. That means this is base 10. We have a log rule that says that when you have an exponent to an exponent, because a log is an exponent, we can bring this thing down. We multiply our exponents. This is x times the log of 4 equals the log of 16384. Because there's times here, to get x by itself, we divide. We'll divide both sides by the log of 4. Put this into the calculator and you end up with x equals 7. To solve for an exponent using logarithms, you take the log of both sides, you bring the exponent down, and you divide. If you are asked to evaluate the log base 3 of 10, most calculators won't do that. Notice you are looking for 3 to some power is 10. What is that? Let's call it x. Remember what a logarithm is. This means, as an exponential equation, that 3 to the power of x equals 10. And we know how to solve that. We just did that on the previous page. We take the log of both sides. Notice now I'm using base 10. I'm not going to use a base. The log of 3 to the power of x equals the log of 10. This is the power rule. I have an exponent to an exponent. I can bring my exponent down. X times the log of 3 equals the log of 10. And we'll divide both sides by the log of 3, the log of 3, and x is the log of 10 divided by the log of 3. You could actually figure this one out in your head. 10 to some power is 10. It's going to be 1. 1 divided by the log of 3. But because this is base 10 now, I can just punch it in the calculator. The log of 10 divided by the log of 3. And the calculator is going to give me a decimal, which I'm going to have to round. And different problems will ask you to round to different places. I'll round to the thousandths, that's 3 decimals. This is about 2.096. If you're observant, you might notice that there's a simple pattern here. The log of 10 divided by the log of 3. Yes, that's the way it works. If I asked you to evaluate the log base 2 of 7, it in fact would be just, I'm going to use plain old log 10, you could use any log, the log of 7 divided by the log of 2, which is about 2.807. The first few questions on your assignment are review, so I'm picking up at question 5. The rest of this video is questions from your assignment. You're going to notice that many of these questions are very, very quick. Question 5, evaluate these. This is base 4. 4 to some power is equal to 4. 4 to some power is equal to 4. Well, that's 1. This next one is 7 to some power equals 49. The log is an exponent. That would be 2. This next one is 6 to some power equals 1. I'm looking for that power. Anything to the 0th power is 1. And the last one is base 10 because there's no base, is 10 to some power is 10,000. Count the number of zeros. There are 4. 10 to the 4th is 10,000. Question 7 involves negative exponents. 2 to the negative 3rd is 1 over 2 to the 3rd. That negative has nothing to do with a negative number. It means reciprocal. 2 to the negative 3rd is actually 1/8. The way we get these to be fractions is by using that negative power. 4 to some power is 64. That's 4 to the 3rd. But because it's 1 over 64, it'll be negative 3. 4 to the negative 3rd is 1 over 4 to the 3rd, which is 1 over 64. For the next one, 2 to some power is 1/2. 2 to the negative 1st is 1/2, because 2 to the negative 1st is 1 over 2 to the 1st, which is 1/2. The next one is also negative 1, because 5 to the negative 1st is 1 over 5 to the 1st, or 1/5. And the last one is negative 4, because 3 to the power of negative 4 is 1 over 3 to the 4th, which is 1 over 81. Question 9. 4 to some power, this is what we're looking for, this is the answer, is equal to 1. Anything to the 0th power is 1. The answer here is 0. A logarithm is an exponent. On question 14, we're looking for the exponent on 3 that makes 81. 3 to the 4th is 81. For the second one there, 9 to some power is 81. Well, that would be 2. For the last one, that's a guess and check one, or we could use logarithms to solve it, like this. The log base 7 of 117,649. I could change base. I could call this x. This means that 7 to the power of x is 117,649. Take the logarithm of both sides. The log of 7 to the x is the log of 117,649. Bring this down. X times the log of 7 is the log of 117,649. And divide by the log of 7. This is the change base rule, but I'm just showing you the steps. Now you could also just guess and check, but we can just punch this in the calculator and we'll know. We get x equals 6, so evidently 7 to the 6th power is 117,649. Write the following as a single logarithm. When do we subtract our exponents? That's when we're dividing. This is equal to the log base 2 of 30 divided by 5, which we ought to simplify to the log base 2 of 6. And there's my answer. Notice here, you're not evaluating that. You're just writing it as a single logarithm. Question 16. Write this as a single logarithm. Logarithm are exponents. When do you add your exponents? That's when you're multiplying. This is equal to the log base 3 of 14 times 7. So we'll simplify that. Take 14 times 7, which is 98. This is the log base 3 of 98. Here we use that property that says when you have an exponent, because a logarithm is an exponent, to an exponent, that we can bring this thing down. This is equal to 5 times the log base 4 of 256. Now I need to figure out what this is, and I could just guess and check. It turns out that 4 to the 4th is 256. So this is 5 times 4. This is 4 to some power is 256. I just tried a couple different numbers in the calculator till I figured out that that thing I needed was 4. And our answer here then is 20. 5 times 4 is 20. Question 24. An exponent to an exponent. Bring the thing down. 6 times the log base 4 of 4. This means 4 to some power is 4. That would be 1. This is 6 times 1, which is 6. For the next one, I'm looking for 3 to some power is 81, and that would be 4. For C here, it's 4, the base, to some power is 64. 4 to the 3rd is 64. For D, we'll do what we did in A. We'll bring this down. 8 times the log base 9 of 9. 9 to some power is 9. That's 1. This is 8 times 1, which is 8. Question 25 uses the idea of fractional exponents. 100, the square root of 100, turns out to be the same thing as 100 to the 1/2. That's because there's a little tiny 2 here that we don't ever put, but it's understood to be there. The cube root of 8 turns out to be 8 to the 1/3. And the fourth root of 64 is the same thing as 64 to the 1/4 power. Now in these questions, we're just using this. A square root is the same thing as a 1/2 power. Try it on a calculator. What we're going to do here then is say that this is the log base 2 of 8 to the 1/2 power. And I'll put this in front. That's 1/2 times the log base 2 of 8. 2 to some power is 8. Well, that would be 3. 2 cubed is 8. This is 1/2 times 3, which is 3/2, or 1.5. The second one, this is the log base 5 of 5 to the 1/2 power. I'm going to bring that down in front. That's 1/2 times the log base 5 of 5. 5 to some power is 5. That's 1. This is 1/2 times 1, which is 1/2. You could also call that 0.5. C, this is the log base 4 of 256 to the 1/2 power. Now, 256 is a perfect square. You could just take the square root of 256, it's 16. We could rewrite this as the log base 4 of 16, because the square root of 256 is 16. 4 to some power is 16. Well, that would be 2. The answer is 2. If you didn't notice what I just did, we could have done what we did with the other questions and said that this is 1/2, bring that down in front, times the log base 4 of 256. And 4 to some power is 256. We just did that on a previous question. It's 4 to the 4th. This is 1/2 times 4, which ends up being 2. There, you got it. D, this would be the log base 3 of 27 to the 1/2. We can bring that down in front. That's 1/2 times the log base 3 of 27. 3 to some power is 27. That would be 3. This is 1/2 times 3. That's 3/2, or 1.5 again. Question 27, the first one uses negative exponents again. Reminder, 4 to the negative second is 1 over 4 to the second, which is 1 over 16. The negative power does not mean it's a negative number, it means reciprocal. That's the way they get the 1,000 in the denominator, and this is base 10. What we're saying here is that 10 to some power is 1 over 1,000. Well, that'd be 10 to the third is 1,000, so this would be negative 3. That's how we get it in the denominator. B uses the fractional exponents again. It's the idea that the cube root of 27, what number times itself 3 times makes 27? This is the same thing as 27 to the 1/3 power. A square root is 1/2 power. A cube root is 1/3 power. A fourth root would be 1/4 power. And a fifth root would be 1/5 power. We'll turn this into the log, there's no base, it's base 10, if you want to put it, of 10 to the 1/3 power. We'll bring that down in front. This is 1/3 times the log base 10 of 10. Take a look at this. 10 to some power is 10. That would be 1. This is 1/3 times 1, which is 1/3. We could rewrite this to make this a little bit easier. The log of 0.1 is the same thing as the log of 1/10. That's 1/10. And this is base 10, so what we're asking for is 10 to some power is 1/10. 10 to the first is 10. The way we get it to be in the denominator is the negative power. This would be -1. In question 29, we get a variety. The first one is negative exponents. 2 to some power is 1 over 16. 2 to the fourth is 16. The way we get it in the denominator is with a negative power, -4. The next one is 12 to some power is 1. Anything to the 0th power is 1. Here we use a fractional exponent. A square root, there's a little tiny 2 there, is a 1/2 power. This is equal to the log base 4 of 1024 to the 1/2 power. We can bring this down in front. This is equal to 1/2 times the log base 4 of 1024. Now this, we'll guess and check on the calculator. It turns out that 4 to the 5th power is 1024. This is 1/2 times 5, or 5/2, which is 2.5. And the last one, this is the property that was in the teaching. This is just 4. You could go back to the teaching and notice the pattern I talked about, but I want you to understand where the change base rule comes from. You can just take any logarithm with any weird base and call it x. I don't know what it is, it's x. Turn it into an exponential expression. 8 to the power of x is equal to 9. Then take the log of both sides. The log of 8 to the x is equal to the log of 9. And bring the x in front. X times the log of 8 equals the log of 9. And divide by the log of 8. Anything divided by itself is 1. X equals, put that in the calculator and round it to 4 decimal spots. It turns out to be 1.0566. 1.0566. One more example, and if you know the pattern, you can skip to it, but I'm going to again show you how it works. The log base 3 is 6. I don't know what that is. I'll call it x. I'm going to turn this into an exponential expression. 3 to the power of x equals 6. I'm going to take the log of both sides. The log of 3 to the power of x equals the log of 6. I'll bring the x down. X times the log of 3 is equal to the log of 6. And I'll divide both sides by the log of 3 and put that in the calculator. Again, notice what it is. The log of 6 divided by the log of 3. The log of 6 divided by the log of 3. That's the change base rule. 4 decimal spots is 1.6309. 1.6309.